No. Okay, start over. Good morning, everybody. This is Sean Downs, Sean for Science from the Pasayten Institute, and today is another great day to talk about mathematics. Specifically, today I'm going to be talking about subgroups of SL2C. Now, why subgroups of SL2C? Well, first of all, SL2C is a group, a Lie group that shows up almost everywhere in physics and other applications of mathematics. Notable subgroups of SL2C include the modular group, SL2Z, or at least some projective version of it, which has a lot to do with a lot of beautiful mathematics associated to elliptic curves and modular forms and that sort of thing. And while it's tangentially related to what we're going to be talking about today I'm going to be focusing on some of the other subgroups of SL2C. Now, in physics, we often talk about SU2, which is a subgroup of SL2C, the unitary matrices. SU2 represents kind of symmetries associated to the weak nuclear force, but also is a double cover of the rotation group in 3 dimensions. And so, as you can imagine, it shows up all the time. Moreover, SL2C is kind of isomorphic to SU2 cross SU2, like 2 copies of it, which gives us in some sense a version of the Lorentz group that we can do particle physics with. So that in and of itself is interesting, but also it shows up in studies of 3-dimensional anti-de Sitter space, which is kind of like Lobachevsky or kind of hyperbolic space, but with a Minkowski metric associated to it. 3-dimensional gravity isn't particularly that interesting as we live in a 3 plus 1-dimensional universe, but it is kind of the prototype model for string theory, as the boundary dynamics of 3-dimensional anti-de Sitter space is directly related to a 2-dimensional conformally invariant quantum field theory. In other words, even at the classical level, this theory of gravity has 2 copies of the Virasoro algebra already present. And so in some sense, SL2C, at least the Lie algebra of SL2C, is the global subalgebra of this two copies of the essentially diffeomorphisms on the boundary. This conversation kind of follows a really cute description that I found on Math Overflow. So bear with me a little bit. To set the scene, let's consider the Quaternions. So you might recall that the Quaternions are a division algebra that's for real dimensions. So you can write it down as like A plus IB plus JC plus DK, where the imaginary unit quaternions I, J, and K all square to -1, and they anti-commute with each other, and so you get like a combination like I times J times K is equal to 1. A representation of the Quaternions is furnished by the physicists' sigma matrices, which we'll represent here as sigma 1, sigma 2, and sigma 3. They follow a similar algebra, and there's an identification that you can make with matrices capital I, capital J, and capital K by simply multiplying these Pauli or sigma matrices by the square root of -1. In that case, you can represent a quaternion element, say Z, either as a sum over these sigma matrices with the identity matrix included, or you can just write it out explicitly, however you like. I wanted to note a few things about these 3 sigma matrices. First is that they're traceless. The second thing is that their Hermitian conjugate is equal to their inverse is also equal to themselves. So in other words, they're self-conjugate matrices. And finally, they form a Clifford algebra. That is to say, their anti-commutator equals twice the Kronecker delta ij. Which means that if I and j are different, they anti-commute, and obviously if they're the same, they commute. Great. So now let's represent a element of the Quaternions in this capacity through a matrix in this way. So, with coefficients, say, zi, and we can take the determinant of that matrix and find a quadratic form written in this way as z0 squared minus z1 squared plus z2 squared plus z3 squared. Of course, if you had flipped over to the ijk basis, you'd get rid of that pesky minus sign. But nevertheless, we see that this determinant automatically gives us a quadratic form that we can interpret, if you like, as kind of like a line element or a metric, or as defining a metric. Now, we want to consider some 2 by 2 complex dimensional matrices, some invertible matrices, some element of GL2C, say G, such that the quaternion matrix, once conjugated by G in this way, gives us another matrix Z prime, and we're interested in the case where this kind of Hermitian conjugation preserves the determinant. That is to say, it preserves that metric, or preserves that line element, preserves that quadratic form. Now, this is true if and only if the determinant of the matrix G is a complex number of unit norm or unit magnitude. So, like, it could be e to the I theta for some angle theta, if you like. And our interest is not with these kind of abelian factors. That's really not what we're interested in. Really, what we're interested in is using this construction to find subgroups of SL2C. And so what I mean by that is we're going to explore a subset of these matrices G, such that one, they're in SL2C, so they have determinant 1, and two, that they preserve kind of like different hyperplanes in that 4-dimensional quaternionic space, or if you like, that preserve different the different matrices, Z1, Z2, or Z3. Good. So to that end, let's write out Z again one more time as a sum over 4 separate matrices, Z0, 1, 2, and 3. And so now let's consider the case of the identity matrix first. So what set of elements G, what matrices G, upon conjugating the identity, give us back the identity? In other words, what matrices preserve this metric? Well, that, given that the identity commutes with everything, is pretty straightforward to see. It's the set of Hermitian, it's the set of unitary matrices, where G dagger G equals the identity matrix. In other words, it's SU2. So by demanding that we fix the hyperplane Z0 in the quaternions, we are asking for the subgroup of SL2C known as SU2, the special unitary matrices. Now, that's kind of intuitive and probably familiar to many of you folks. So let's compare this case with a hyperplane defined by the Pauli matrix sigma 3. So what matrices G conjugate sigma 3 and bring us back to sigma 3 that preserve, in other words, sigma 3. Sigma 3, you might recall, is a diagonal matrix in this basis, and the diagonal elements are 1 and minus 1. So if you think of the identity as the kind of the metric on C2, giving you the typical quadratic form Z1 squared plus Z2 squared, it's clear that SU2 should respect that metric. But what about sigma 3? If we interpret sigma 3 as a metric, what we're actually looking for are not the matrices in SU2. We're actually looking for matrices in SU1, comma 1. And actually, that's how this entire story got started, at least from my perspective, as I was looking for a concrete representation of matrices to describe SU1, 1. Why that would be the case is a great story for another day. But anyway, as you can see, the line element associated to SU1, 1, that is to say, the line element associated to sigma 3 is just Z1 mod squared minus Z2 mod squared. What I'm going to do now is complete the identifications of all of the various fixing hyperplanes and defining subgroups. Just simply state what they are, and then I'll go through the process of actually computing them for the 3 cases that are not SU2. So good. So once again, if we fix the hyperplane Z0, we get the special unitary matrices, SU2. If we fix the hyperplane Z1 with the Pauli matrix Z1, we get the subgroup SL2R, kind of the split real form of SL2C. If we fix the hyperplane Z2, we get the real symplectic matrices in 2 dimensions, which is another interesting case for physics there. And finally, if we fix sigma 3 again, we get the matrix group SU1, comma 1. Okay, great. So how can we go about constructing the representations explicitly? We're going to do this at the level of Lie algebras, since A, that's what I was interested in, and B, I think that's what will make things most clear. So you might recall that the Lie algebra of SL2C has real dimension 6 and can be parametrized by those physicist sigma matrices, those Pauli matrices sigma I. So let us write a generic element in the Lie algebra as a kind of a sum, a linear combination, a complex linear combination of the sigma matrices. And clearly they're all traceless and invertible thanks to the definition in terms of these sigma matrices. And our 6 real parameters are basically the real and imaginary components of the 3 complex parameters that we've discussed. Now, to break SL2C down to any of the other subgroups that we've just mentioned, we need to find a way to select 3 of those parameters out of that total of 6. Now, instead of having 20, 6 choose 3, right, 20 real parameters, really what we also want to impose is a requirement that we also have each of the sigma matrices present. So we need to, in other words, we need to pick a coefficient for sigma 1, sigma 2, and sigma 3, and they can either be imaginary or real, and we just need to pick 3 of them. So just quick combinatorics analysis is easy to see that we can pick all 3 to be real. We can pick 2 of them to be real. We can pick 1 of them to be real, and we can pick none of them to be real, giving us 1, 3, 3, and 1 respectively. Now, one thing worth pointing out here is that there's a kind of an additional symmetry in the sense that if we picked all the real coefficients or all the imaginary coefficients, the resulting subgroups are actually related. They're related, and similarly for the case of 2 real or 1 real, they're related by kind of the standard group homomorphism that takes us from a physicist's description of a Lie algebra or a Lie group to a mathematician's description of a Lie algebra or a Lie group. That is to say, we multiply by I, right? So in reality, we only have 4 subalgebras to consider. We only have 4 sets of generators to consider: the case where they're all real and the case where 2 of them are real. So consider some matrix G represented as the exponential in the Lie algebra with coefficients q sub I, where q is either strictly real or I times a strictly real number. Now, regardless of our choice of q, we know that because the sigma matrices form a Clifford algebra, we can see right away that if we were to commute sigma I with e to the, say, alpha sigma I for some real parameter, or for whatever, some parameter alpha, that those 2 objects commute, no big deal. Whereas if it's sigma I times some operator e to the alpha sigma j, where I and j are different, what we actually end up with is a minus sign in the exponential. And so we for all practical purposes, if alpha is real, you end up getting the inverse matrix. And so this Clifford algebra construction really helps us see how the math works out really cleanly here. Good. So if all of the coefficients are real numbers, so we write the whole thing as e to the, say, I alpha 1 sigma 1, I alpha 2 sigma 2, I alpha 3 sigma 3, we get back SU2, and that's pretty much familiar. So for the rest of the 3 cases, we're looking to choose one of the hyperplanes to leave invariant, sigma 1, sigma 2, or sigma 3. And in that case, we let sigma 1, sigma 2, and sigma 3 be the real parameter. That is to say, in the matrix exponential, it's e to the I alpha sigma I, say. And then we're picking the other 2 parameters of associated to sigma j and sigma k to be imaginary, strictly imaginary numbers. And this will always guarantee us to give us the operator that preserves that hyperplane. So to be precise, let's look at preserving the hyperplane generated by sigma sub I, one of the 3 Pauli matrices, and we can construct the operator G given as the exponent of the quantity e to the I theta sigma I plus alpha sigma j plus beta sigma k, where j and k obviously are not equal to I, and alpha and beta are real numbers. Good. So choosing sigma I gives us the different representations of the different subgroups that we're interested in, or at least the Lie algebra they're in. So once again, if you pick sigma 1, you're getting SL2R. If you pick sigma 2, you're getting the real symplectic group in 2 dimensions. And if you pick sigma 3, you're ending up with SU11. Great. So that was just a bunch of fun goofing around with some of the matrix subalgebras of SL2. This has a lot of implications to a lot of stuff related to physics and to the vertex operator algebras discussion that we're having on one of the other playlists in this channel. So please do check that out if that's at all interesting to you. We'll go back and talk about how these different subgroups might play roles in other kind of interesting mathematical and physical objects in future videos. So I'm just going to leave it here for now. Thank you so much for watching. Have a great day.